Hello everyone, my name is Guy Katz and I'm a PhD student at Professor David Arell's research group at the Weizmann Institute of Science. In this video, we're going to see a short demonstration of a wise computing framework that we are currently developing. Wise computing is a pretty big project, so our work to date by no means implements it fully. However, our initial results are quite promising, and I hope that this video will give you an impression of what wise computing is all about. As we explain in the paper, a wise computing framework is aimed at making developing reactive systems easier, quicker, less prone to error, and most importantly, more fun. The framework is designed to be both interactive and proactive, and is meant to be regarded as another member of the programming team doing its best to help improve the product that's being developed. Now, in our tool, the wise computing framework is actually divided into three major components. The first component is called Athena. Athena is an offline tool and is intended to be run during the system development. She uses formal analysis tools to learn conclusions about the systems for the benefit of the programmer. The second component is called Regina. Like Athena, Regina is also an offline tool, but the difference is that she uses semi-formal methods, and basically her strategy is to run multiple simulations of the system and to look for interesting properties that the programmer may or may not have had in mind. Consequently, her conclusions may not be as accurate as Athena's, but she is more lightweight and can thus better cope with the state explosion problem. Finally, the third piece is called Livia. Livia is an online tool, and hence her name, used for live debugging of the system that's being developed. She is used to help the programmer in finding and understanding bugs in real time. In the remainder of this video, we're going to see how the three components, Athena, Regina, and Livia, help us develop a small application. In this part of the demo, we're going to see a demonstration of Athena, the first of the three components, and you'll recall that Athena handles offline analysis of the system using formal methods, so she produces accurate conclusions. I'm going to start by demonstrating the sample application that's going to be our running example. So I'm just going to run it and explain as we go. So this application implements a price dispenser machine. So it's a very simple machine that has three levers, one for numbers, 1, 2, and 3, a lever for letters, A, B, and C, and a lever for colors, red, green, and blue. And the idea is that the user can configure the three levers to any configuration, and then hit the check combination button. Now, if the machine is properly configured, this will give us a price. Otherwise, nothing will happen. So let's configure the machine to configuration 1, C, and green, and hit check combination. And you can see that nothing happens. So this window here on the back prints out the log of the events that were triggered. So this basically describes the run so far. Now let me configure the machine to configuration 3, C, and blue, which is the correct configuration, and then hit check combination. Now we get a price because this is the correct configuration. So this is the very simple application, and it's implemented using behavioral programming, which is a framework for developing reactive software using scenario-based programming. And I'm not going to tell you much about BP in this demo. If you're interested, you can read more about it online. I'm temporarily going to comment out the price dispenser thread, which handles dispensing of prizes. So now the machine can never give us any prize. And now this is the wise computing framework is built so that with every compilation of the code, Athena gets a fresh copy of the program and starts to analyze it. So this window here is Athena's output window. Typically I have it on my second screen. I just moved it here for the sake of making this demonstration. Now I'm compiling the code. So in a second we'll see Athena beginning her analysis. So it's important to understand that the code doesn't have any special annotations. Athena doesn't know anything about this specific application, and the first thing that she does is to construct an abstract model of the code. So for instance, you can see here that she has identified all the threads of the program, sensor, logger, and the three lever threads. And she attempts to characterize these threads using their characteristics and things that she can figure out without any annotations. So for instance, the logger thread was characterized as an actuator thread because Athena saw that it only prints stuff to the screen and doesn't really affect the program. The threads that implement the three levers were characterized by Athena as array cell threads. This means that these threads have a sort of memory inside them. So for instance, the color lever, Athena tells us that if we hit blue, then it will retain the value check blue. So basically we can look at the value that is stored within the color lever. Likewise for the other colors and likewise for the other levers. Now, Athena also looks for optimizations and unused code. So for instance, she tells us now, and remember that this is Athena, so everything she says is exact, that the three lever threads do not appear to be in use, and we should consider removing them. Recall that right now, this is so because the price dispenser thread is not being used. Let's reinstate it and compile again. Okay, I'm just clearing the screen. And now we expect Athena, so now she tells us that no optimizations were found, because now everything is in use. Another thing I wanted to show you, let's go to the price dispenser thread. This thread basically, again, I'm not going to explain the code, but it checks that the letter lever is in position C, that the number lever is in position 3, and the color lever is in position blue. And if everything applies, it dispenses a price. Let's suppose I made some error when I was programming this code, and instead of checking the 3 levers, I checked that lever number 2, the number lever, is in configuration 3 and also in configuration 2 at the same time. So obviously this is impossible. Let me recompile the code. And let's see what Athena has to say. So now she tells us, she recognizes that the color lever is now not being used, remember, because it's currently commented out. And she even tells us that thread price dispenser has an unreachable state. This encodes the state of the thread, but basically this thing here tells us this is line 48. So if I go to line 48, this is precisely this line that dispenses the price. So Athena tells us that this state is unreachable in the code. Of course, looking for unreachable code is just one out of many features that Athena supports, and we're going to see a few more interesting examples later on in this demo. In this part of the demo, we focus on the second component of the WISE development suite, namely Regina. Recall that Regina, much like Athena, operates in an offline manner, that is, she is invoked every time that the code is compiled, but unlike Athena, she doesn't employ formal methods in order to derive conclusions, but rather she runs semi-formal methods and mostly simulations of the system in order to come up with interesting conclusions. So here is the output from Regina, and I'm going to compile the code. Let's have a look at what Regina has to say. So recall that when we run Athena, she creates an abstract model of the system. So this model is shared with Regina so that she can run simulations on it. And you can see that she begins by running simulations on the system up to a certain length. And then she starts coming up with emergent properties. These are properties that Regina recognizes in the traces of the simulation that she runs, and she thinks they may be interesting to the programmer. So for instance, events check 1 and check 3 have strong correlation. That is, they appear close together, or they appear in similar frequencies. And Regina consequently checks whether these two are really linked. Now, check 1 indicates that the number lever is pointing to 1, and check 3 indicates that it is pointing to 3. So we don't really expect them to be connected. So Regina checks possible emergent properties, namely that they are always connected or that one of them implies the other, and she arrives at the conclusion that these emergent properties do not hold, which makes sense. So there are a bunch of other properties that she checks, and none of them hold, so this is not very interesting. But eventually she comes to one that does hold. So here it is. There's a strong correlation between check blue and dispense price. This makes sense because when we dispense price, we check that the levers are properly configured, and the last check before the price is dispensed is that the color lever points to blue. So these are the emergent properties, and Regina finds out that yes, check blue and dispense price always appear together. But now there's even a more interesting twist. So remember that Athena recognized that the color lever is an array cell thread. It adheres to this design pattern. So this is the read event, but there's a write event. The setting of the lever to blue is the really interesting event. So Regina knows this, and she says, event check blue is an array read event. The matching write event is blue. Blue indicates us setting the lever to blue. So the really interesting emergent property is that dispense price implies that the lever was set to blue. Then there's even another step. So because the color lever is an array cell and there were other connected array cells that had a similar form, so Regina checks if dispense price event is connected to additional array cells. And then she is able to come up with precisely the interesting emergent property that the price can only be dispensed if we set the lever to blue and we set the letter lever to C and the number lever to 3. So this is precisely the so-called correct property for this system. And depending on the configuration of the WISE development suite, these properties can also be passed on to Athena to be formally verified. Right now, this is just a semi-formal analysis that indicates them, but this form of analysis is often better in combating state explosion. So Regina is more scalable than Athena. For the final piece of today's demo, we're going to have a look at Livia, the third component of the WISE development suite. Unlike Athena and Regina, Livia is an online tool. That is, she isn't invoked during development with every compilation of the code, but rather the developer may choose to trigger her when trying to debug the system or running the system in order to determine if it's behaving correctly. So in order to demonstrate Livia, I've added a new thread to the system called prize limiter, and this thread guarantees that the system can only dispense 3 prizes. Once 3 prizes have been dispensed, no additional prizes will ever be dispensed again. Let me run the system. And now let me fire up Livia. Livia is our debugging assistant. So here she is. She has connected to the program, and now she will monitor what's going on. So it's a bit crowded on my screen, so I'm going to put Livia aside for a while. And now let me start dispensing prizes. So I'll configure the machine to the correct configuration, and I'll start clicking check combination. So we see a dispense prize event has been triggered. Another dispense prize event has been triggered. And the third dispense prize event is triggered. But when I click check combination again, no more prizes will be dispensed. Okay, so this is behaving as intended. And now let's see what Livia has to say. So Livia has been keeping track of the system, and in particular, she has been keeping track of the situation of all the threads. As I continue to click events, Livia is basically noticing that the thread prize dispenser is stuck at state S5 for quite some time now. And as soon as this is going on for a while, she will alert us by saying that thread prize dispenser appears to be stuck at state S5 for a while. Should she investigate? Now, if I click no, she'll do nothing, but when I click yes, what happened here was that Livia launched Athena in order to perform bounded model checking around this state of the system, the current state, in order to see if there's a sequence of events that can release it. So if she had found anything, she would indeed show us the sequence of events that we needed to trigger in order to release this trapped thread. But as it is, she is able to determine that the thread is indeed stuck for good.